So in this lesson, we're going to talk about still some more volume, but to start off, let's talk about everything we have been discussing over the last couple of videos that you've watched. Here's a region, again, pretty much a common function here, this rational function 1 over x. We should know what that kind of looks like. We'll go off a highlight here. There's a rational function. Again, another boundary is y equals 0, otherwise known as the x-axis here. X equals 1, that's a vertical line, and x equals 4. So again, your job in doing any volume question is to first identify the area of the region, which this is already shaded for us, which is great. And so we're just running through a couple of things here. What I want to do first is find an integral that represents the area of region R. So that means I don't have to actually evaluate the integral, but I do want to set up an integral that represents area. So I'm going to set up area and think, okay, well, I'm going to draw a rectangle in this image, and I can either do top minus bottom or right minus left. And I usually start with top minus bottom because I'm just more comfortable with that vertical presentation. And I just kind of take a look and make sure that everything is consistent. So the top endpoint is going to be on that line, y equals 1 over x. And the bottom endpoint, no matter where I slide that rectangle, it's always going to be anchored on the x-axis. So that is consistent. So this is a great way to set up the area. Now, if I set up a vertical rectangle, that means my integral is going to be in terms of the x variable. So I'm going to set this up, and I'll switch back to my color here and say, well, it's really just the integral of top minus bottom dx. Okay, now my limits of integration, again, I'm finding those along the x-axis. I'm starting at x equals 1, I'm ending at x equals 4. So the area integral, I would have the integral from 1 to 4. The top function is whatever this y equation is, right, which is 1 over x. And the bottom function here is y equals 0, right? You can kind of label those ordered pairs. Top minus bottom will be y minus 0, which I'm going to, I guess I could write like that, but we know that kind of looks silly. I'm going to translate that for this question. Y is 1 over x. So that is my integral that represents the area of that shaded region. Okay, now part B, we're going to use the same shaded region, and now we're going to write an integral expression that represents the volume of the solid formed by revolving this region over the x-axis. So I'm going to get in here, maybe actually we'll use a highlighter here, and I'm going to bold out this line. This is now my spinner for part B. And this is where I'm going to kind of be revolving around. So this is what I'm spinning around. And if that's the case, that rectangle I already have in here looks pretty good in terms of a disk method problem. So I can move over to my volume set of skills here and say this is disk method for volume. And so because I have that rectangle drawn in a vertical presentation, my integral is going to be pi on the outside, little r squared dx. Now again, my limits of integration are going to come from the x-axis. And what I need to know here is what r is. So r is the length of that rectangle. And so again, that's pretty much just top minus bottom. So let's put it in terms of this particular question. The volume is going to have a pi on the outside, integral from 1 to 4. I'm squaring that top minus bottom. You're squaring 1 over x. That's your setup for the volume. It just said an integral expression that represents the volume, and so you can move on. Okay. Now we'll take a look at part C, where part C is asking for another volume, but this time we're going to find the volume by revolving about the line y equals 2. So I will try to choose a color that stands out. Maybe I'll use orange. Let's see how that does. All right. So we're going to revolve around y equals 2. So I'll go back to my picture. Maybe I'll try to get rid of my last spinner, right? Let's get rid of all of those. And let's put in my new spinner at y equals 2. Okay. So I'm spinning around here. And now if I keep this, little rectangle, this vertical presentation that I had before, this is fine. It's perpendicular to the axis of rotation. But notice it's not touching the axis of rotation this time. And that's how I know this would be a washer scenario. So let me go through and try to rework this whole problem on a washer method situation. So for the washer method, remember you need a cap R and a little r. Let's fly down here and write it out. So for washer method, that's where you have a pi on the outside, and it's the integral of cap r squared minus little r squared. Now again, this is drawn vertically for this particular problem, so that's why I'm going to have a dx. So my limits of integration, again, are going to be from 1 to 4. But let's address what cap r and little r are in this picture. So cap r is the point furthest away from the axis of rotation. I want the distance from the axis of rotation to that furthest away point. So remember that you're always going to develop this distance, in this vertical setting as top minus bottom. So that length for cap r is actually consistently, 2 minus 0, because any dot up here is at y equals 2, and any dot on the bottom of this rectangle is y equals 0. So it's not even variable. Cap r is a fixed value of 2. Now little r is changing. Okay, so little r is the distance from the innermost point to that axis of rotation. So that distance in there is little r. So when I try to represent what little r is, that is changing, that is variable. And so that is going to be 2 minus whatever that y coordinate is. It depends on where exactly in this region it is for what the value of little r is. So little r is 2 minus y. So I'm going to kind of use those two things. I have cap r basically as just 2, a fixed number, and I have little r as a variable expression, 2 minus y. So I'm going to put that in my integral. There's my volume. My limits of integration go from 1 to 4. Cap r we said was just 2, and little r we said was 2 minus y, which looks really weird because my integral is supposed to be in terms of the x variable. So I'm going to make my switcheroo move right here and switch that out. I can also say that 2 squared is 4. And this is a good integral setup to represent that volume. So of course you could crunch the numbers on all of these and come up with a numerical value. For sure, these are all doable. It's worth noting here that on part A, your antiderivative involves the natural log of the absolute value of x, just for talking about actually evaluating that. Notice here on part B, your antiderivative is really involving a power rule. You're adding 1 to the exponent and dividing by your new exponent. So just worth noting that those are very, very similar looking integrals, but they have very different looking antiderivatives. You have a good amount of algebra work that you'd be facing on part C. But again, all of these are doable. You have the mechanics to do it. But I just wanted to kind of review some of the stuff from the previous lessons while we tackled a new problem. So our new problem is this one down here. Let's write an integral expression that represents the volume, but this time we're going to revolve a line around the line x equals 1. So let's fly up to our picture. And let's think about this, because if I draw in the vertical line, x equals 1, we didn't do anything weird like this before. If you think about this, we've got a little bit of an issue here, because all I know how to do in volume right now is to draw a rectangle perpendicular to the axis of rotation. And this is a problem for this particular section, because you've got this breaking point here, like right here. I'm just going to kind of draw this line in. If you're above this line, if you draw your rectangle perpendicular, then what you've got here is you've got the right endpoint on y equals 1 over x and the left endpoint on that vertical line. That's great. If you're below this line in the sand that I've drawn in here, and I try to draw a rectangle perpendicular here, it's kind of hard to see, but what you would have is, well, my right endpoint is now on the fixed line of x equals 4. You'd have two different methods going on here, or two different integrals, I could say. Same method. It would both be disk method, But you'd have to do two separate integrals to represent this volume. And so I don't really like doing two integrals if I can avoid it. There must be a better way. There has to be a different way of thinking about it, and there is. So we're going to go on to the next page, which again is the same region. I just basically am going to physically tackle this problem. I sketched the problem by hand just to exaggerate some of these ordered pairs, kind of blow up the picture so it's easier for me to see. So again, that line in the sand of like something strange is happening right here. That's the weird moment where you would have a disk method here, right? And you would have a separate disk method here. When I keep talking about things being consistent, this is not consistent. See, that right endpoint has changed in those two situations. That's what I would like to avoid. You can certainly do it this way if you want to, but it's certainly not efficient. And I'm definitely going to ask you questions that are going to require a new method. So let's just undo all of that orange that I put on here. Okay, and so let's come up with a different structure. So let's take a look at what the shell method is. So the shell method, what I'm going to do is I'm going to draw a rectangle parallel to the axis of rotation. That's different because for disk and washer, remember, it's perpendicular. And whether it's touching or not touching, that's what distinguishes disk from washer. Here in the shell method, we're going to totally change our frame of reference, and we're going to draw that rectangle parallel to the axis of rotation. Now, that is going to create a different geometric shape. It is going to create a cylindrical shell. So I am going to draw a rectangle parallel to the axis of rotation. So again, let me highlight. I will actually use a highlighter. Let's highlight what our axis of rotation is. It's x equals 1. Let's do that. Let's put our spinner around it. There's where I'm spinning. So I want to draw a rectangle that is perpendicular. I'm sorry, parallel. I just got done saying that. Parallel to my axis of rotation. Oh, there it is. And so if I move this rectangle left or right, it stays consistent, meaning that top ordered pair is on 1 over x, and the bottom endpoint is on the x-axis. So that is consistent whether you move it left or right. Okay. What I want to do is think about what do I create. If I revolve it around x equals 1, let's actually imagine doing that. What you're creating here is a little cylindrical shell, right? That's my best artwork there. So you've got this like cylindrical shell kind of coming along. It's hollow on the inside. So imagine like a soup can where you've taken off the lid and the bottom. You know, just with a can opener, you just kind of took off the top, took off the bottom. That's what I mean by a cylindrical shell. So I'm going to redraw this cylindrical shell over here on the right. Okay, so I'll draw it. Got this big hole in the middle, but you've got this cylindrical shell that you're kind of working on. Let me put the spinner in there. And what I want to do is talk about the volume of this cylindrical shell. So let's think about the object that we really have in play. What I'm going to try to do, as you've seen in some of these other descriptions, right, is I want the width of this rectangle to be really small, so thin, you know, like a tuna can. You can't even really see the width of the aluminum, just barely. I want it to be even thinner. I want it to be as thin as a piece of paper or thinner than that. So really that's what I mean by this, the thickness here. This is pretty exaggerated. I want this to be really, really thin so I could barely even see it. What I'm going to imagine is I'm going to imagine coming at this thing with a pair of scissors, and I'm going to cut it. I'm going to cut right up the side of this soup can or tuna can. I'm going to roll it flat. So when you do that, you do create a different geometric shape. If you cut it and roll out that aluminum, you would actually just basically have this piece of aluminum, you know, on your kitchen counter that has some kind of length to it. right? And it has some kind of width to it, and it has some kind of, if I can, I don't know, show this, has some kind of depth to it. All right, if you could roll out that aluminum on your kitchen counter. So let's talk about the volume of this. Notice that I'm not talking about a cylinder anymore. I'm talking about, really, this is, in geometry terms, this is a rectangular prism. I know how to find the volume of this cylindrical shell. And I'm going to label it like that. So let's say we're going to find the volume of a cylindrical shell. What it is just, well, a rectangular prism, length times width times that extra dimension of depth. So let's get in here. Let's think about what that length is, right, along this top edge, this guy right here. That's actually coming from, again, you cut up the side of this can and then you laid it flat. This here is that length along the top. That also, let's undo that, whatever happened there. That is a circle. That's how long around the circle did you actually go? So again, in geometry terms, that's the circumference of that circle. So let's think about the circumference of a circle. It's 2 pi r. So let me label my diagram and say, well, I have some kind of radius length to that circle there. So that's what the length along the top is, by the way. The length is the circumference of that circle, 2 pi r. Now, we're also going to relabel the width. We're going to call that h, like, hey, what's the height of that rectangle? And then I have this extra dimension of depth. So I'm going to put all those puzzle pieces together here in the volume of this cylindrical shell. So 2 pi r is what translates to the length. We renamed the width as h for height. And then we have this extra dimension of depth. Now keep in mind that extra dimension is that thing that I want to get really, really, really thin. That is the thing that I really want to get closer and closer and closer to 0. That thing is going to tend to 0. So I'm going to, again, take this idea and say, look, what if we didn't have an exact value? I would just say, well, let's just find all the volumes of these cylindrical shells and I'll add them together. Let's say I did 10 rectangles. It would be better if I had 100, or better if I had 4,000, or 100,000. So we're going to jump right to the exact value of the volume here and talk about it that way. So the volume, and we're going to say exact volume. We're not going to get into any approximation speak here. Exact volume by shell method it looks like this. I am going to have an integral because you're really taking the limit as the depth goes to 0 of the summation of all of these volumes, right? But I'm going to get right to it and say, look, what do I have? 2 pi is just a coefficient. That can come outside the integral. What I have left to really get in here and figure out is r and h. And then the depth, that's what's going to translate, and I'm going to just put it all together here. It's either going to be a dx, that thing that goes to 0, if you had a rectangle that was drawn vertically, or that depth is going to be a little dy if you drew that rectangle horizontally. There's so much consistency through section 7.1, 7.2, and 7.3. If you draw a vertical rectangle, you are doing an integral in terms of x with a dx. And if you draw anything horizontally, you have an integral with y's and dy. It's the same thing here. So let's reestablish what r and h are. Okay, so let's just put this down here. Like, okay, let's do this. So r and h, right? Let's actually state what they are. Where r is actually the distance from the rectangle to the axis of rotation. So let's take a look on our picture here. That's what r is. Like, here's your rectangle, and it's the distance of that rectangle to the axis of rotation. Let's see what it is on our image here, right? It would be the distance from this point to that axis of rotation. Okay, now h, right, let's kind of go here, right? We said that the width was h. Well, this is h. What that is I'm going to call that the length of the rectangle. So r is the distance from the rectangle to the axis of rotation, and h is the length of the rectangle. So think top minus bottom or left minus right, right? So that's what we have going on. So if I go to my picture, this distance is h. Now, I want to make sure that you realize you're always going to be going either top minus bottom or right minus left, because you want all of these positive values. It's very important with the shell method that you have a positive expression. All right, so when it comes to this particular problem, when I am going to set up, okay, well, I'm going to do shell method. I clearly see that I drew that rectangle in parallel to the axis of rotation. I'm going to represent r. I already have it marked off, but it's right minus left. This is any random x coordinate anywhere between 1 and 4, but I'm subtracting it from that boundary, which is 1. So r in this case is a variable expression. It depends on where you draw it, and it's the x coordinate minus 1. It has to be in this order. You can't write 1 minus x, because 1 minus 3 is negative 2. That would be the wrong order. Subtraction order matters, and so it's very, very important that you write it that way. When you think about h, think about that. That's a top minus bottom scenario. I'm thinking about the length of that rectangle. So what do I have? Well, this is any random x coordinate, but the y coordinate is 0. Your top minus bottom here is difference in y coordinates. It's y minus 0. Now, sometimes this looks, I'll just throw it together now, like I'll put it in our shell method formula, and it looks kind of ridiculous, but I'm going to do it anyway. I'm going to say 2 pi, I've got r, which is x minus 1, I've got h, which is y minus 0. This was drawn vertically, so it's going to be a dx, and I let this sort of drive the rest of the show here. That dx, again, is a powerful statement that tells you you should be looking for your limits of integration along the x-axis, that you're going from 1 to 4. But I'm not even set up yet, because this is ridiculous that I have both an x and a y variable in my integrand. That should not be. What I'm going to do instead is replace what y is in terms of x. And y is 1 over x. So I'm going to make that swap. Now, if I asked you to set up an integral that represents the volume, this would be it. This question did, in fact, it did say write an integral expression that represents the volume, so I will box it. This is an integral expression that represents the volume. If I say, which I'm going to, let's find the volume, that means you have to come up with a numerical answer. And I don't think I've said this in any of the other videos, whenever you're doing area and volume, your answer has to be positive. If you crunch the numbers and you end up with any final answer that is negative, there is some kind of mistake in your work. I don't know if it's an antiderivative mistake or a setup mistake, but there has to be a positive answer to doing this. So let's actually crunch the numbers. Let's handle this. Let's actually, I'm not going to do a u substitution. I can very easily, distribute that 1 over x to the x and the minus 1. So I'm going to do that. So x times 1 over x is 1, and then minus 1 over x. And then here are my antiderivatives, right? I would have x minus the natural log of the absolute value of x. And I'm going to work on that fundamental theorem. Now, absolute value of 4 is just 4. And let's see what we have here. And that's just a 0, so I guess I can write plus 0. So let's get this stuff together. The final answer here as a number would be 2 pi times, let's just say 3 minus the natural log of 4. That's your exact answer. Numerically, that's a little more than 10, but you would need a calculator to know that. But I do have a positive value. Don't be annoyed by this minus natural log of 4. If you check this on a calculator, it is something that is positive. And this is the exact volume. This is coming up with the actual volume, not just the integral that represents it, but the actual volume. It's exact. It's not it is not an approximation. Okay, so in the next video, we'll go over some more examples of this. But what I want to sort of end this video with is thinking about, disk and washer is where you are drawing a rectangle that is perpendicular to the axis of rotation, and shell method, you're drawing a rectangle that is parallel. So sometimes people kind of think about the wording, like shell, parallel, they kind of sound the same. And so if you think about perpendicular, if you just kind of think about saying it a little bit wrong and say perpendicular, perpendicular is disk and washer, and parallel is shell.